Okay, so let's get started. So I'm going to be talking about risk, minimum risk training, and reinforcement learning. This actually makes it really hard for me to present, also, because I always look at that screen and present. Um, so. Okay, so first I'm going to talk about something that we're very familiar with, which is maximum likelihood training. And maximum likelihood training is predicting the next word in the reference given the previous words as a way of, or predicting the next action given the previous actions, if we want to make it in a more general framework. And here I've used F and E, but if you view F as X and Y, E as Y, then this is our normal, P of Y given X. And we decompose this in the into action by action prediction in a locally normalized model like we do normally. So this is the thing that we're very familiar with, right? And this is also called teacher forcing because you're forcing in, or you're feeding in the correct examples every single time. And this has a couple problems. The first problem is exposure bias, which we've talked about before. So this assumes you're feeding in the correct previous inputs, but at test time we may make mistakes that propagate. So exposure bias is that the model is not exposed to these mistakes and can't deal with them at test time. Another problem is that this disregards our final evaluation metrics. So like as I mentioned before, likelihood will give equal weight to multiple wrong predictions, right? So like let's say we have a really wrong prediction like turning a verb into a noun in part of speech tagging, and a somewhat wrong prediction like turning a verb into a past tense verb. It would give both of these equal weight, and that's not good. And in text generation or parsing or other things, we also have sequence level metrics like a BLUE score or a Meteor score for text generation, or maybe F1 measure for parsing or something like this. So we would like to measure according to this, and some mistaken predictions will hurt more than others. So to give a very stereotypical example of this, let's say we're trying to generate a 50-word sentence where like about 50 words would be appropriate in the output. Let's say we make a mistake predicting the end of sentence symbol instead of something else after the first word. Now suddenly we have a one-word sentence, which is really bad given that we were expected to generate a 50-word sentence. So maximum likelihood estimation or likelihood prediction would give that really bad mistake the same weight as other mistakes. Okay, so I'm going to talk about error and risk. So I've already talked about error a little bit, but just to talk about it one more time, so we can get onto the so that it's in everybody's minds. Error, basically, what we want to do is we want to generate an output. So we take our argmax of our output given our input, or some other generation function, which I'm going to be talking about next time. But for now, let's assume that we're generating an output given the input like this. We calculate its badness. So this is, if we have a score of goodness, like a BLUE score or a Meteor score or something like this, then we would calculate our error as 1 minus that value. It could be 1 minus our accuracy of a part of speech tagging task, 1 minus F1 score of a parsing task, for example. And we would like to minimize this error. But one of the reasons why this is non-trivial to optimize is because the argmax operation is non-differentiable. So the argmax function makes discrete 0-1 decisions about what thing to output next. And because of this, the gradient of the argmax function that we basically, it's a little bit different from this, but basically the argmax function looks a little bit like this, right? It looks like a step function where, the moment we transition from one thing being the max to the other thing being the max, it will have this immediate change. And everywhere else, the gradient is 0, right? So we can't easily optimize over this. Yeah, what I said. Okay, so risk. What is risk? Risk is basically the expectation of the error. So the expectation of the error looks like this. So we have the error function here defined over all of our possible outputs e tilde, and we also have the probability of this e tilde given the input in the parameters of our model. And so so this has a nice interpretation. It's basically like how poorly do you expect to do given this model, given that you have a true reference. And notably, this includes the probability directly in the objective function. It includes the probability here. And fortunately, this is now differentiable, or this now has a direct path from the objective function to the output, or from the objective function to the parameters, because the parameters directly appear in this risk function here, right? So this is differentiable, but like before, our sum here is intractable, right? So there's no way we can enumerate over all of the possible outputs. So what minimum risk training attempts to do is instead of attempting to optimize the log probability directly, it attempts to optimize this risk, basically. And the way you do this is you sample a subset of the outputs. So you create a small sample of sentences, 5 to 50 or so. So this sounds very familiar from last week, right? Where I was talking about sampling or taking the argmax or something. And you can calculate the risk over that. So basically, this S here is our small sample of 5 to 50 outputs. I keep saying sentences because I talk about this in the framework of translation or text generation, but it could be any other structured output that we want to predict. And we can create these samples using random sampling or n-best search. So this is relatively straightforward. The difference here is that we are calculating a probabilistic objective as opposed to some of the non-probabilistic objectives we talked about last time, right? So we were talking about margin-based objectives, et cetera. This is now a probabilistic objective where what we're trying to do is we're trying to minimize the error, the expected error of our outputs, which I guess is also good, right? Because what we want to do in the end is optimize this error, because that's what we're going to be evaluated on. We're going to be evaluated on our BLUE score, our METEOR score, our F1 measure, et cetera. And this is just kind of a probabilistic interpretation of this. So I went over this. Yeah, sorry, go ahead.
What is the Z there?
So that's a good question. So the Z is a normalizing constant. There's two ways you could think of using this Z. The first way you could think of doing this is by just normalizing over all of the outputs that you could possibly be considering. Another way is by normalizing over all of the outputs in your sample here. So what that would look like is you would have a sum over E tilde in S, and it would be probability of E tilde given F. And then this would be your normalization constant for S, basically, like this. The method in Shen et al. Uses this normalization constant over just the things in the sample. I've actually never tried it the other way. I've tried it with the normalization like in the sample, but I've never tried it the other way. So I don't know if the other way works, but I suspect it doesn't, because it would only make the method simpler, and they didn't do that. They did this. So this is a very simple way to probabilistically train your model for an error function. I have a very simple quiz, which is, this has a very strong connection to likelihood-based training. What is the connection to likelihood-based training with respect to this here? And specifically, if you need a hint, if you set the error function, the connection to likelihood-based training becomes very clear. Set the error function to a particular value. Any ideas? I heard somebody say something, but yeah.
The error function is like a log function, kind of resembling some crossing.
So if the error function is a log, let's see. No, not exactly. You might be getting this in the other direction actually. But any other ideas? So what if you set the error function to be 0 most of the time and 1 in some particular cases? Any ideas? No? But what's that? It would be the maybe not exactly. Maybe I'm phrasing this quiz so it's too hard. But basically, if you set the error function to be 1, if e tilde is equal to e, and 0 otherwise, this probability of e tilde becomes the probability of e, right? So you sum over everything, it becomes everything other than the probability of e itself, the error becomes 0. The probability of e itself becomes 1. The error, no, okay, sorry, it's the other way around. It's this. There we go. So so now the probability, if the probability of e itself becomes larger, this error will become smaller. If the probability of anything else is high, then the error will become larger. So basically what this is saying is, if you want to maximize the probability of E, the correct answer, and you want to minimize the probability of anything else, and you don't really care how anything else is. So if you think about what log likelihood does, it's also similar, right? Log likelihood is trying to maximize the probability of E itself, or minimize the negative log probability of E itself, and minimize the probability of everything else. So basically, what I want to say here is that this error, or this risk is very similar to the likelihood function if this error is equal to this 0-1 loss, where you get an error of 1 if you get anything wrong, and you get an error of 0 if you get everything correct. However, like as I mentioned before, some things are not, some mistakes are bigger than others. So getting all of the words wrong in an output sentence is worse than getting just one word wrong in an output sentence. Or getting, the phrase structure completely incorrect is much worse than getting the phrase structure like one off error or something like this. So there's a strong connection between this risk with the error function being equal to the 0-1 loss and other things. Maximum likelihood. Okay, so, oh, sorry, I didn't have the mic on. I didn't realize this. Is this better? Yeah, okay, thank you. Okay, so I talked about sampling. So another thing that this Shen et al. Paper does is they add a temperature. to the minimum risk training term. And the reason how they add the temperature looks like this. So basically it's raising this to 1 divided by tau. And this is, that's also included in the normalization term. So this is like 1 divided by tau down here as well. So what this temperature adjusts for is it basically adjusts for the fact that you're only getting a small sample of the actual outputs. And in reality, like if you're normalizing like this over this small sample, everything post-normalization. So like to give an example, like let's say we have our highest probability thing is 0.01, and then 0.05, 0.003, etc. After you do normalization, this gets a very high value of like 0.666, 0.333. If you only took the top two. And so because of this, this value is very large. However, if the highest probability value is very large, however, if you included a much larger sample, this value would be much closer to 0.01, right? So what this normalization term does is usually what they do is they try to make this distribution more flat. By setting it to have a high temperature. And what that does is it basically makes the difference between the top one and all the rest smaller. And that helps compensate for the fact that the denominator is much smaller because we're normalizing over not enough outputs. So this is a very, very important detail. If you actually look at the paper that proposes this method, if you don't set this to the correct value, it doesn't learn very well at all. So I thought it would be worth mentioning it. But if you're not using minimum risk training, then you might not need to worry about this.
So,
Yeah.
what deduplication?
Oh, I skipped this. Okay, I'm sorry. So deduplication basically if you're doing something like reinforce, it's a little bit of a different story. But here, if you do random sampling with replacements, so if you do random sampling and you could potentially get two of the same outputs, then you might accidentally sum over the same thing twice. So you might accidentally get P of E tilde given F, where this corresponds to the same sentence. And that's not an appropriate way to train using this this method. So sorry, that's also kind of a fine-grained detail here. But anyway, like the most important thing here, these are kind of details, but the most important thing here is like what is risk? Risk is the expected error, and we want to train our models to minimize this risk. And the reason why we want to train our models to minimize this risk is because we actually want to train them to minimize error if we're doing argmax decoding on the probabilities anyway. So we'd actually want to train them to minimize error, but that's not differentiable, so this is a good proxy to it. So that's the overview of this session, of this section. So why am I talking about these at the same time as talking about reinforcement learning? And the reason why I'm talking about this at the same time as doing reinforcement learning is actually reinforcement learning is attempting, at least probabilistic methods for reinforcement learning are attempting to do the same thing. They're attempting to maximize reward, which in turn is minimizing risk, right? So it's just a different view towards the same problem in some cases. So, so what is reinforcement learning? I mean, we had this in the reading, but basically it's learning where we have an environment X, an ability to make actions A, we get a delayed reward R, and we get a delayed reward R. So this is kind of the definition of reinforcement learning. The example of Pong, X is our observed image, A is up or down, and R is the win-loss at the end of the game. So why would we want to use reinforcement learning in natural language processing? I think there's a lot of different reasons why we would want to do this. Um, so this is the minority of cases in NLP, but there are definitely cases where we have a standard reinforcement learning scenario. So the standard reinforcement learning scenario is, for example, a dialogue with a human where we make responses and we get a reward at the end. So this is like the first application of reinforcement learning to NLP. It's still one of the most successful applications. But for example, a call management system where you call in to try to get technical support for your plane ticket that you had to cancel. So they have a automatic speech recognition system. They have an automatic language understanding system that tries to understand your utterances and fill in slots and stuff like this. And at the very end, it checks whether it has gotten all the way to actually performing a modification to your plane ticket. And if the answer is yes, and it says, like it asks, were you satisfied with this call at the end? And the person says yes, that's a positive reward of 1, right? And maybe it's modulated by how many turns it took to get to the very end. Another example would be like you have a robot command and control task where you tell the robot to do something, and then you have some measure of success where the person says, were you happy with my performance? And they say yes. So, so we do have examples like this. Another example is when we have a model with some sort of latent variable. So this latent variable could be something like, let's say we're doing a question answering task over all of Wikipedia, and we have a double, we have a 2-stage process. One stage process is information retrieval, where we get the most relevant Wikipedia article. The second step of the process is question answering, where given the, given the article, we then try to actually answer the question. So in this case, we have a latent variable, which is which article should we be choosing to try to answer this. So in this case, we have a latent variable, and we need to get a reward based on the configuration of the latent variables. Then finally, we might have a sequence level error function, such as blue score, which we cannot easily optimize without first generating a whole sentence. So this is another widely used application. This is what I just talked about with minimum risk training, for example. And so all 3 of these are examples of where people have used reinforcement learning. These are listed in decreasing necessity to actually use reinforcement learning. So for the first one, we definitely need to use reinforcement learning. It's just a reinforcement learning problem. There's no way around it. For the second one, we might be able to come up with some proxy where we don't have to use reinforcement learning. It might also be that we can use instead some sort of search-based structured prediction algorithm. We can use incremental rewards of some sort. We can do many, many different multiple rollouts. We can search from different points in the latent variable search process, for example. So there are ways around using just a straight up reinforcement learning algorithm. For the last one, we actually may have much better ways of optimizing this than using reinforcement learning. So I wanted to emphasize that first. Yeah.
Is there a reason why we shouldn't try the last one? Because typically you'd be optimizing for, say, sequence level error when you're doing a sequence level prediction. So why would we not use it?
Why would you not? Well, so why would you use that instead of, for example, some sort of search-based structured prediction algorithm that I mentioned in the previous class? And maybe a margin-based method with some sort of dynamic oracle type thing would work better and be more stable than a typical reinforcement learning thing where you just roll out all the way to the end of the sentence. I'm going to talk about this a little bit more later also, but I think like straight up reinforcement learning where you just roll out to the end, get a reward at the end, and then propagate it back is going to be not be a good choice, but maybe some tricks plus a reinforcement learning algorithm would be an okay choice that would be competitive with the other options. So, yeah, good question. Any other questions? Okay, so supervised MLE, sorry, I'm showing this again, but supervised MLE, basically we're optimizing the log probability or minimizing the negative log probability. In the context of reinforcement learning, there's a concept called imitation learning. And imitation learning is basically where you want to imitate a teacher that teaches you how to act in an environment. And so MLE is one variety of this imitation learning, and there's a lot of other work on imitation learning that you could look up if you're interested in this. Things like Dagger that I talked about last time are also methods for imitation learning. Dagger, which is also called scheduled sampling. So that's another thing that came from the imitation learning literature. So I guess the main reason why I'm mentioning this is if you want to read RL papers, you can realize that these are similar concepts. So next is self-training. So self-training, basically, you can sample or argmax according to the current model. So basically, you get an output y hat according to the current model, and then you use this sample or samples to maximize likelihood. So basically, instead of maximizing likelihood according to the true output, you maximize the likelihood according to the generated output. So one really nice thing about this is you actually don't need any correct y, right? You're just optimizing towards y hat. So that's really good because maybe you have unlabeled data. But what is the problem here? Any ideas? It's kind of obvious if you think about it a little bit. But yeah.
So you had a degenerate case in this, and you would also be equaling the probability towards that. Say you had a degenerate case, so you would kind of just get stuck over there.
Yeah. So degenerate case are bad output, right? You know, like let's say you had an output that was just bad. And you would just be increasing the probability of the bad output all the time, right? So there are some successful alternatives to this. So one alternative is co-training. And the idea of co-training is basically like you have two models, you do self-training, but you only use the places where the models agree, right? So you have your transformer model, your LSTM model, and you only take the cases where the models agree and self-train on those. So this also has, like, I talked about distillation, I think, in this class already, didn't I, or not yet? Maybe not yet. Okay, there's also a concept of distillation, and distillation is basically where you take a large model, you generate outputs from the large model, and then you train on these outputs from the large model for a small model to try to train a small model. Or you might take an ensemble of models. So 10 models. You generate an output according to the 10 models, and then you train another model based on this. So the idea here is you have like a better model, and you want to train a smaller, more efficient model. So that could also be a little bit viewed in a similar perspective as well. So like if you take an ensemble, generate it according to an ensemble, and use that ensemble output. So there's a nice paper called Sequence Level Knowledge Distillation that talks about how you do this. Another interesting result is actually a paper by one of the students I'm working with, Junshin He, who has a recent paper that shows that actually if you do self-training, you can go a long way by noising the input. So you take the input and you also add noise to the input as well. And basically what this says is you have a noisy you have a noisy output because your model makes mistakes, but if you also make the input noisy, that helps prevent overfitting to these mistakes that you might have in the output. And this was surprisingly successful. I wouldn't have expected this to work as well as it did. But that's a nice recent paper that's going to be coming out at iClear very shortly. So, yeah, but anyway, so that's just kind of a prelude. So when we get into policy gradient or reinforce, what we're doing is we're adding a term that scales the loss by the reward. So we have the negative log likelihood, but we're multiplying this by the reward, basically. And sorry, this should be L reinforce or something like that, not L self. And basically, outputs will get a bigger reward if they get a higher weight. So again, here's a quiz. Under what conditions will this be similar to or equal to maximum likelihood estimation? Any ideas?
Reward is one for all of these.
Yeah. Reward is one for what?
For all of you.
No. Reward is one when... Any ideas? I have a hint over there. Yeah? Y equals y hat. Yeah, so basically reward is 1 when y equals y hat, but reward is 0 in every other case, basically. So if you remove the fact that we're going to be having to sample trajectories and say, we could sample like an infinite number of trajectories, basically the negative log likelihood of the correct answer will be multiplied by 1, and the negative log likelihood of everything else will be multiplied by 0, so we can just ignore it. So again, a 0, if we're talking strictly about like using it for sequence generation or something like this, then this would be an example of how we could use this. However, if our reward function isn't, or like if there is no gold standard reward annotated in our data set, or no gold standard trajectory annotated in our data set, obviously we couldn't do this in the first place, and we'd have to sample trajectories, evaluate them, and see what the output looked like. Okay. So this was covered in the reading. I'm not going to go through it to like much more than this, but are there any questions about this? Okay. Credit assignment for rewards. And this is actually really important if you want to train a model that is trained purely using reinforcement learning. So how do we know which action led to the reward? And this is kind of like the big problem. I would say this is the big problem in reinforcement learning. It's the reason why reinforcement learning is harder than purely supervised learning. So the best scenario is that we basically get immediate reward. So if we're getting an immediate reward like this, we do A1, A2, and then we get an immediate reward of +1, which like directly corresponds to A2 being something useful. Then this is good because now we know that, hey, A2 was probably a good example. Then we do A4, we get -0.5. Etc. And then at least we know that all of the actions we took up to A2 were the things that led us to get a positive reward. All the actions we took up to A4 were the things that led us to get a negative reward, etc. The worst scenario is we only get it at the very end of training. So like we get a reward of +3, but we don't know, A1, A2, A3, A4, A5, A6. We don't know which one of these was like responsible for getting this at the end. So if we do this, basically the model has to jointly infer that A2 was a good action, or which action was good, which action was bad with respect to getting this reward, and update the model parameters. And we often assign decaying rewards for future events. This was covered in the reading as well. This is kind of the background for reinforcement learning style training methods. The big problem with applying reinforcement learning to NLP tasks, the big problem with applying reinforcement learning overall is like other sampling-based methods, so like other methods where we're sampling a subset of the potential things we could output, reinforcement learning is unstable. It's particularly unstable when using a bigger output space. So like, for example, if we're doing text generation, our output space is all of the words in a vocabulary. So our output space could be 60,000 at each time step. And that makes this a really hard learning problem. And we need to use strategies to stabilize this. So compare this to Pong, right? Compare this to the Pong example. Pong, we had two actions. One action was up, one action was down. if you have a simple action space like this, it is actually pretty reasonable to just do end-to-end reinforcement learning training. And eventually you will get a positive reward. But if you're training with, if you're training over 60,000, it's just going to be really hard to get any reasonable reward out of an action space at large from random sampling. So our first strategy is adding a baseline. So the basic idea is we have expectations about our reward for a particular sentence or particular action. So let's say we wanted to do translation, where one example of a sentence is the sentence, "This is an easy sentence." The second example of the sentence is "buffalo, buffalo, buffalo," where the first buffalo is a noun, the second buffalo is a verb, and the third buffalo is also a noun. Buffalo means to be very stubborn and try to force somebody into doing something they don't want to do. So you can imagine a buffalo doing that to another buffalo. Anyway, actually search this on Wikipedia. The actual sentence is buffalo, 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 buffalo. So that's a real grammatical English sentence. But so anyway, we have our reward of 0.8 and 0.3 for how well we process the sentence. But actually, "this is an easy sentence" is an easy sentence. So we should have been able to do really well. We should have been able to do 0.95. So buffalo, 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 we have 0.3 and 0.1. And so if we look at how well we did with respect to our expectations, actually for the first sentence, we underperformed. We did worse than we expected. For the second sentence, we overperformed. We did better than we expected. So instead of assigning a reward for the actual baseline, we can assign instead of assigning the reward for the actual reward, we do baseline minus reward. And sorry, this is actually backwards. It should be B minus, wait. One of them is switched. It should be reward minus baseline. Yeah, so that's correct. That B minus R up there is wrong. Okay. So how do you estimate this baseline in the first place? The easiest way to do it is to take your model and the representations your model has learned, just feed them into a linear regressor that tries to predict your reward for each sentence. Or no, actually, sorry. I'm going to talk about this next. So the choice of the baseline is arbitrary. So one thing you can do is predict the final reward using a linear regression from the current state, either for the whole sentence or for any particular example. So you could predict the baseline for the whole sentence, or you could predict it each word one at a time, and predict the output. So this has shown to be relatively useful. Another thing that you can do is you can use the mean of the rewards in the batch as a baseline. So let's say you have a batch of 32 sentences, and you know that over training, basically your average reward is going up like this. So basically what this is saying is your reward started out very low at 0, and then it's going to 1. So basically by taking the average reward in the mini batch, that's saying, given this entire mini batch of text, how well do I think that sentences included in this mini batch are doing? And am I doing better on this particular sentence than I'm doing on other sentences? And this is particularly useful, for example, if you're doing bucketing and sorting by length, for example, because longer sentences might be harder or easier than shorter sentences. So if you have similar sentences in your mini batch, that also helps as well. The nice thing about this also is it's non-parametric and completely stable. So I've had better success with the bottom one than the top one. Unfortunately, I think the bottom one is not actually theoretically correct. It's not a theoretically correct way to, it gives you a biased estimator. It's not an unbiased estimator of the risks. So it works well, but might not be ideal. Okay, yeah.
I'm actually not clear with
So it's this B here.
Yeah, but what do they mean by calculating? Like what exactly is to have that baseline?
Oh, so the baseline, basically, you try to estimate what you would expect your reward would be for that sentence. So in any case, if you're training a linear regressor to predict the reward for the sentence, you would train a linear regressor to try to predict the reward that you actually got after doing your rollout. So like you would do your reinforcement learning, or you would do your rollout, you would get your reward, and then you would try to predict that reward given a linear regressor from like the encoder, for example, or maybe the decoder or something like that.
But then wouldn't they ideally be trying to learn, like fit onto the baseline rather than fit onto like the actual task at hand? Because now we're minimizing our like the risk that is there with respect to the difference of these two. So we're trying to technically fit onto that, and which we kind of have already calculated rather than, because maybe in a hypothetical scenario, having a reward of 0.8 over there is beneficial because the parameters are set so that we get a better reward on the first game.
Well, so okay, there's two ways to predict baselines. The first one, or there's two ways to calculate baselines that I mentioned here. One of them is training a regressor to try to predict the reward. In that case, your regressor is trying to predict the reward. It is trying to fit something that goes from the input features to the reward. However, that's not the model that you're actually training. Like that's an auxiliary model. The actual model that you're training is trying to optimize this this B minus R function here, basically. So it's trying to increase it, or sorry, R minus B function. So it's trying to increase its reward with respect to the baseline. So you're trying to train the model to basically give you a good output for this is an easy sentence or buffalo, 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 or something like that. So
Isn't this kind of like we're trying to match the trade placement?
no, you're trying to do better than the baseline. Yeah, so you're trying to get the positive reward here as much as you can, and that will the best way to do that is to do better than the baseline. So another way to look at this is if you take option 2, you're trying to train your model to upweight action sequences that gave you a reward better than what you were doing right now, and downweight action sequences that gave you a reward that's worse than like the average of what you're doing right now. So because of this, like basically you want to upweight good action sequences, and that's what the whole goal of reinforcement learning is in the first place. So,
Because the thing that confused me is that when they're really close to coming to the baseline and also become so small that we won't actually have even big updates.
yeah.
So as a result, I'm not sure that even though technically this is unbalanced, like say here or something like that we have increase in one direction. But still around 0 we have like almost negligible upgrades that will kind of make it stuck around the point.
Okay, so that's a good point. One thing is when your predictions are very close to the baseline, your reward becomes very small, which I agree with. That would be the case if you did this. Another thing that you can do is, in addition to subtracting the mean, you can also divide by the variance. And that makes sure that your rewards are always within the same scale for the entirety of training. However, that might not be ideal because like as you start getting up here, maybe legitimately your variance in reward is very small. So like right at the very beginning, maybe none of your outputs are very good, and then you kind of like to maintain that principle. But as you get to the end, you might not want big fluctuations in reward unless legitimately you got something that was just a lot worse than others, and you want to penalize that. So, yeah. Good question, sir. Okay, so so regarding question 3, the reason why I despite the fact that the reading mentioned if you never get a positive reward, then you can't learn anything. In fact, if you get only negative rewards, as long as you have a baseline, you can still learn from the relative goodness of the model. So, like one example of when you would only get negative rewards is sometimes you will have a model where you try to generate P of Z given X, and you sample a Z from this. I'll call it z tilde, and then your reward is the negative, or is like the log likelihood of your output given, given z. So this is your reward. And this is very common in like a reconstruction loss, for example. So you, maybe if we set y to x itself, this is basically like something like an autoencoder where you generate one out in output z, and then you try to reconstruct the original input from the output z here. And this is a very common method for training or trying to learn latent variables or something like this. You could view BERT as an autoencoder, right? It's trying to reconstruct the original input given a noise version of the original output. You could also do that for latent variables. So like, let's say you want to do style transfer or something like this, which we're going to talk about later, which is you want to translate positive sentiment articles into negative sentiment articles for whatever reason. You want to, like, AstroTurf Yelp or something like that. Don't do that. That would be a bad idea. No, seriously, like, don't do that. That's a very bad idea that you should not be doing. But like, so you have style transfer. You have style transfer where you want to turn positive sentiment articles into negative sentiment articles. So you could have X be a positive sentiment article, Z be a negative sentiment article, and then want to reconstruct the positive sentiment article, and then you have this reconstruction loss. But note that this is always negative, right? Negative log probability, or log probabilities are always negative. However, if you have an appropriate baseline, you could have this reward be positive when you did better than all of the other examples at reconstruction. Even though all of the scores are negative, the less negative score would be your best reward. So you can learn that circumstance. But you won't be very effective unless you have a baseline in that case. Okay, another thing is increasing batch size. So this is very effective in kind of any sampling-based training strategy, but it's particularly effective in like reinforcement learning scenarios I've found. And each sample is basically higher variance for the reasons I explained last time. Instead of enumerating all the negative examples, you just have a few examples that you're trying to increase or decrease the probability of. So what you can do is you can either increase the number of action sequences or rollouts for a particular example. So like in other words, instead of sampling a single z, z tilde, given p of z given x, you could sample z tilde number 1, z tilde number 2, z tilde number 3, etc. And what this is good is this controls your like your in sample variance or your in sentence variance or something like this. Another thing you can do is you can just update over many different sentences x before you, or wait to do an update until you've processed many different sentences x. So this is the traditional kind of view of mini batch, right? So in mini batch training, you normally do 32 sentences at a time or 64 at a time or more if you really want to. So you can either have the number of rollouts for each sentence be larger or the overall mini batch size be larger. And both of these are effective at stabilizing. Another thing that you can do if you want to save time is save previous rollouts and reuse them when you update the parameters. So this is something called experience replay. And the basic idea here is that you don't necessarily generate new trajectories or new rollouts every single time. You can keep some around. There's two reasons why you would want to do this. The first reason is that it's faster, basically. You don't have to actually calculate the rollout. You don't have to do sampling, so you can just keep it around and use it. The second reason is that, for example, let's say you have a really bad reinforcement learning model that does this, right? So you have a really bad reinforcement learning model that just has fallen into a pathological solution of doing your style transfer task by translating all outputs into horrible, which is a very good way to maximize your negative sentiment, but not a good way to get good reconstruction. So if you fall into this pathological situation, then you're never going to be able to recover it because you're never going to be generating anything other than horrible. But if you're doing experience replay from a model that actually did have half-decent outputs, then that will prevent you from like falling into this pathological thing and not being able to escape. So that's another good thing to know about. Okay, any questions? Okay, yeah.
Does MRT also have like the issue of like credit assignment that reinforcement learning also has because you get the reward for the entire?
Okay, very good question. Does minimum risk training have the problem of credit assignment? Yes, it does. It does have the problem of credit assignment. However, it shares a commonality with. So minimum risk training, you have to do, especially if you're normalizing, you have to do multiple rollouts because you need to calculate the denominator. And if you only had a single rollout, the denominator would be equal to the numerator. It would cancel to 1, and you wouldn't get any gradient from it. So minimum risk training is always done with multiple rollouts. One of the advantages of multiple rollouts is if they're very similar, only the places that changed will be like essentially assigned responsibility for the differences. So if you only have one word that's different between the two and one gets a large, bonus and the other doesn't, then it will know basically that that's the part that was responsible. That's the same for reinforcement learning with multiple rollouts per sentence. So I think that's one thing that kind of helps credit assignment, but not completely, because like, what if your rollouts are completely different? Then you have no guarantees. Yeah. Good question. Yeah.
Just a follow-up question about the never getting positive rewards.
Yeah.
Thing. If you have a baseline, then you're rewarding the things that were not as bad.
Yeah.
But if you have no baseline at all,
Yeah.
that would be avoiding the things that were worse more. Is that equivalent?
So it is technically equivalent, yes. In reality, though, it is not a very good way to train your model. And the reason why is because you're penalizing everything you generate, right? Like every single thing you generate will be penalized to some extent. So if you have a huge action space like vocabulary of 60,000 words times sentence length, if you're penalizing every single thing you generate, then that's just gonna, you're gonna degenerate into like, that will definitely ensure that you go to a really horrible place of the space and you can never escape. So if you're doing something with only negative rewards, having a baseline is the only reasonable way to like explore the space effectively and kind of hill climb in the appropriate direction. So it's basically the difference between ruling out all of the bad things by process of elimination versus actually, encouraging the good things. So if you have 60,000 to the 30 possible things to explore, you don't want to be doing the process of elimination. Let me put it that way. Yeah. Yeah. Question.
So instead of risk minimization, I think we can directly approximate the risk function using the neural network. So in the case of blue logic, we can easily make the translation estimate the blue stable.
Is that for credit assignment? Are you talking about for credit assignment?
And not credit assignment.
Yeah.
So I have some. I'm just talking about some another way to minimize the risk. So instead of using RL, why don't we approximate the risk directly using the neural network?
Well, so minimum risk training that I talked about before is one alternative to using RL, and they're both optimizing the same function. They're both trying to minimize the risk. They just do it in slightly different ways.
I mean,
Oh, approximate the risk using, or approximate the blue score or something using a neural network. There are ways to do this. There's something called professor forcing, which is like teacher forcing, but the basic idea is that you try to predict the cost of the output from like the hidden states before you make any decision about the outputs. And there's also other things like Gumbel softmax or things like this. I think we're going to talk about these in the future. And basically all of these things, what they're trying to avoid is they're trying to avoid the fact that argmax is non-differentiable and trying to backprop directly into something that is differentiable within the neural network. I'm not talking about them this time. I haven't found them to be super effective for MT or sequence generation related things for reasons I can probably talk about later, but it is another option. So I think that's kind of beyond the scope of what I'm going to talk about this time, though. So, yeah. Okay. So another thing is warm start. So if you have a method that you can train with maximum likelihood, so like let's say you're doing machine translation or you're doing parsing or something like this, and the only reason why you want to use RL is to optimize a sequence level evaluation metric like BLUE or F1 score, you already know the true answer, so you can just optimize towards the true answer first, and then you just reinforce after that. So Mixer, which is one of the first applications of RL to sequence generation using neural networks, basically gradually transitions from MLE to the full objective. So they talk about a schedule. So to recap, when to use reinforcement learning, if you're in a setting where correct actions are not given and the structure of the computation depends on the choices you make, yes, you don't have any other choice but to use RL. If you're in a setting where correct actions are not given, but computation structure doesn't change, this is what I just talked about. There might be some sort of differentiable approximation. I won't be talking about that this time, but I'll be talking about that in the future. If you can train using MLE but want to use a non-decomposable loss function, maybe yes, but there are many other methods that you could be using, like max margin or min risk, and you can also use those as well. So to talk very briefly about, I'm starting to run out of time, so I'll go very briefly through the other parts. But there's also value-based reinforcement learning. And value-based reinforcement learning, basically policy-based learning is like reinforce. We try to learn a good probabilistic policy to act in a, that maximizes the expectation of the reward. Value-based learning basically tries to guess the value of the result of taking a particular action and take the action with the highest expected value. So we have something called the action value function. So given a state S, we try to estimate the value of each action A. So it's the expected reward given that we take that action, like this. And this is, it's often called Q learning as well because you use the name Q for this, this function. For example, in a sequence model, the state could be the input and the previous generated words, and the action would be the next word to generate. And you would essentially try to predict the expected reward based on this. You then take the action that maximizes the reward, like this. So notably, this doesn't have to be a probabilistic model with respect to calculating this value function. You do have a probability in the expectation here, but this doesn't have to be a directly probabilistic model. So how do we estimate value functions? If you've taken an RL class, the first thing you did, like one of the first things I did in my ML class in my undergrad was do Q learning, or not first things, maybe one of the last things I did in my ML class in my undergrad was to do Q learning where we had a taxi driver that drove through a grid world and you got a reward from the results that the taxi driver took. And this is tabular Q learning. And this is basically you remember the Q function for every state and action pair, and then update that every time you do a rollout. So it looks a little bit like this. It's basically like gradient descent on this Q value. But the neural, the big problem here is that the state action pairs are too sparse. You can't have, for example, a sequence generation task. You can't have every single previous prefix and every single word in your output be explicitly memorized. So what you can do instead is you can take a neural network and approximate this. So you just basically train a neural network to approximate. This Tesoro et al., or Tesoro 1995, does anyone know what this paper is? This was before AlphaGo beat humans at chess. At Go, before Deep Blue beat humans at chess. This was beating humans at backgammon. So this was the first like human parody in like board-based strategy games result, and it was done with neural networks. And then neural networks went out of fashion, so Deep Blue didn't use neural networks, and now they're back in fashion, so AlphaGo uses neural networks. But anyway, so one of the problems here is exploration versus exploitation. The problem is if you always take the best option. So if you always, take the option that you think gives you the higher expected reward, the moment you get a positive reward from any of your, action sequences, you're going to be likely to, make that action every single time, right? So this is less of a problem with stochastic policy-based methods where we randomly sample actions, but here we're taking the argmax, so that's a problem. And one solution is every once in a while we randomly pick an action with a certain probability, epsilon. So this is called the epsilon greedy strategy. Another thing that you can do is you can use an intrinsic reward, which basically gives a reward to models that discover new states or new looking states. I think this is very interesting because basically what it's saying is you want to get reward, but you also want to try new things. And I kind of feel like this is what humans do also, right? We want to try new things. We don't necessarily know if they're going to work, but it's just kind of exciting to try new things. And I think babies, do this all the time, right? So this is a powerful method, and it can be, incorporated in policy gradient-based methods as well, if you want. Yeah. So finally, very quickly, to go through a few examples of reinforcement learning in NLP. Dialogue was one of the first major successes in reinforcement learning. There's a very nice survey by Young et al. 2013 explaining all of the ways they've applied it to dialogue. They used Markov decision processes, which I didn't really talk about a whole lot here. But they also had a concept of something called partially observed Markov decision processes, and these are ways to reason under uncertainty in your underlying outputs. And the reason why is in dialogue, very often you will be doing spoken dialogue through a telephone or something like that. So you have upstream potentially wrong speech recognition results that you need to deal with. So you deal with uncertainty of that. Now there are neural network models for both task-based and chatbot dialogue. This Williams and Zweig paper is very nice. It demonstrates how you can train basically a mixed mode or like a full task-oriented dialogue agent using neural networks to solve Google Assistant or Bing Assistant in this case, because they were from Microsoft type tasks using APIs. So I recommend that. In dialogue, this was also ahead of its time in with respect to using simulators. So they use simulators to simulate a user. So they would build basically a user that had a set of underlying intentions, and that user simulator would act based on these intentions. And the reason why this is good is because now you can interact with your environment infinitely, right? You can, but there's hidden information from the dialogue agent. It doesn't know what the underlying intentions are, so it has to elucidate them through dialogue. So it learns how to communicate in that way. Yeah. So this is an example. You set up like the intention bar beer central. and then the agent has an idea of, or like it has information. The agent asks, hello, may I help you? And then the user simulator has an intent, and you generate the utterance based on the intent. Another thing, this was really far ahead of its time. I think this is a beautiful piece of research by Regina Barzolet's group at MIT. And they created a model for following commands in Windows, like the operating system, the environment. And basically the way it works is they have a weak reward signal where they have a bunch of instructions about how to use Windows. And then they set up a Windows environmental simulator where you could act within this environment by pressing buttons or typing text or things like this. And your weak reward signal was whether the next thing that appeared on the screen, so like for example, this menu, sorry, this is hard to read. This menu item appeared on the screen, and whether that matches any of the other things in the instructions. So you get a reward if you know what to do next, basically, because you have text overlap with the output. So I think this is an awesome paper. They also applied this to other games. I think they applied it to Civilization, the game, and learned how to play Civilization. I don't remember if it was exactly Civilization, but I think that's very nice work. There's also visual instructions with neural networks. Misra et al. Has a nice example of this as well. Incremental decisions in machine translation. So this is an example of our work, and also some by Graham et al. At University of Maryland. So we had a task of simultaneous translation, where basically you want to start generating output as soon as possible, given an input. And the motivation is you want to translate speech, but you don't want to wait until somebody finishes saying a sentence before you can start translating. Because if you're saying a really long 50-word sentence, kind of like the sentence I'm saying right now, it will take a very long time between the beginning of the sentence and the end of the sentence, and you wouldn't be able to translate before then, and people would be left behind, right? So that was maybe 50 words in that sentence. So, yeah. So basically what you learn is you learn when you can start translating and still get good results. For example. Another one is information retrieval. This is also by Regina Barzolet's group, but they find evidence for an information extraction task by searching the web as necessary. So they get an article and they get information from the article that they want to extract. If they have a really hard way of getting information, like a couple and 4 children, how many children are there? They instead search the web for other articles that talk about the same incident. And some of them say 6 people, and so that information is easier to get. Finally, course-defined question answering. I already talked about this, but this is basically you have a long document, you want to do QA with an expensive model, you do reinforcement learning to get a subset of the text in the document, and then use your expensive model over that. Finally, RL to learn neural network structure. I think I talked about this before in the recurrent neural networks thing, but basically the idea is you generate a whole bunch of neural network architectures and you figure out which one works best for your task, and that's your final reward. So this is neural architecture search. Okay, so I ran out of time. That's why I kind of breezed through the last ones, but hopefully this was interesting, and I'll see you on Thursday. On Thursday, I'm going to talk about search. I think this, I redid my slides for Thursday. I think they're good, so I hope you show up, even though there's no quiz. See you later.